No. Just say next, I will move it for you. Don't worry.
Okay. Okay, so next, please. Well, so my presentation has two parts. The first is just to introduce the International Institute of Refrigeration, the type of activity resources that they have. And the second part, this is mostly to go to the heat pumps and energy recovery activities, and to see what is the challenges and opportunities of these heat pumping technologies. Just to revise, to summarize that what is the contribution of you see in the last month in August, we IAR organized the International Conference on Refrigeration in Paris. So that means I will show what is the topics and related with this field of the heat pumps and energy recovery. So the next, please. So the International Institute of Refrigeration, it was founded in 1998, and this is the only independent intergovernmental science and technology-based organization promoting knowledge of refrigeration and all associated technologies like heat pumps. So this is this is a big network. There are around 60 member countries that belongs to the to IAR, and accounts with over 400 experts in the different fields, discipline, and with more than 500 corporate and private members. So next, please. So all the activities of the IAR are coordinated by the Science and Technology Council. So these activities are divided into 10 commissions, which are organized in 5 sections. So section A, this is on cryogenics and liquefied gases, and has 2 commissions, A1, A2. The section B is for thermodynamic equipment and systems, and also has the corresponding 2 commissions for the topics. The section C is the biology and food technology, section D, storage and transport, and section E, air conditioning, heat pumps, and energy recovery. Well, particularly the Commission E2 is focused on heat pumps and energy recovery. And in the last 8 years, I was the president of this commission. In the conference, in the frame of the conference of the refrigeration congress, that IAR organized every 4 years. All the staff, the officer, they are renewed. So that means that I finished my mandate in August of this year. So the next, please. So the IAR participate in different with different organizations, and this is some intergovernmental organizations that are well known, like the UNEP, or there are the Food and Agriculture Organization. So that means that this is quite common. You will see after in the projects that the IAR are involved, that some of them they are funded and or are in collaboration with these institutions. So the next, please. Yeah, but also IAR is collaborating with professional organizations. This is like Israel, but also Israel is very active, in these collaborations. Also, there are European organizations like the German DKB or the French AFF. So that means that this is quite common, and you will see also in the projects that they are under development, that there are some that they are developed with Israel. So the next, please. Yes, what is the activities? Well, and the and the information resources, no, that IIR is doing. No? So the first interesting, this is a database. No, FreeDoc is a database for refrigeration information with more than 100,000 scientific and technical references. This is very interesting database because it contains all the proceedings of most of the conferences that they are related with refrigeration. Some of them, they are the IAR conferences, but others, they are the co-sponsor conferences. So that means that this is a very nice and very good organized database. So the other information resources that is also very important, this is the International Journal of Refrigeration. This is a peer-reviewed online scientific journal published by for IAR by Elsevier. Well, you have there what is the impact factor that is growing, no? So that means that this is an important information resource of IAR. But there are other documents that they are produced in the frame of IAR. This is like the IAR newsletter that all the members, they receive monthly with important information. Also, IAR published some books and guides, informatory notes, international, also there is the International Dictionary of Refrigeration, that this is available online. There are, as I mentioned before, the IAR conference proceedings that they are also available, the expertise directories, the training courses. So that means that every time there are more and more information that this is available in the website, no? That this is a very, it was renewed, I think the last 2 years ago. So that means, well, and here you have some examples of this type of documents that they are produced. For example, this is the informatory notes. This is a very brief document with some information about some current and different topics, no, that they are of some interest, and they are well, and all the commissions are producing this type of informatory notes during the period, no, that they are, that mostly there are 5 years period, no, sorry, 4 years period when they are planning all the activities, and you will see after that there are some interesting informatory notes that they are producing. So please, the next. So there, here there are some research projects that IAR are developing. So this is, you see that there are, as I mentioned before, some are with the World Bank, other with the United Nations Environment Program. But particularly, this is one that this is could be of your interest, and this is the project ND+. Because yesterday they were presenting, no, some papers, some communication of related, no, with this program, no. So that means that this program has aims, no, to demonstrate the CO2 refrigeration technology in India in different high energy demanding sectors. So yesterday we saw, no, that there were some prototypes that they were developed for the marine applications and other for other sectors, no. So please, the next. Well, here there are also some other projects that they are funded, no, in the, for example, by the European Union or other programs, no. So please, the working groups. This is also a very interesting activity that they are developed in the frame of the different commissions. So that means that these working groups operate in a temporary basis. So that means that they are continuously creating, or some of them, they are finished their activity. And this is here to bring together specialists to collaborate in projects focused on current refrigeration issues. For example, you have here some of the working groups that at this moment they are under development. This is, for example, dehumidification, inner conditioning. For example, this is the refrigeration system safety, that this is related with the hydrocarbons and the use of the hydrocarbons in the refrigeration and heat pump systems. There are also other like the whole body cryotherapy on cryostimulation, the other more classical that the PCM, the phase change materials. So that means that there are all even some new or related with the emergent technology, refrigeration technologies that the solid state heating and cooling systems. So that means that we go to the next, please. Yeah. So also IIR has organized a series of conferences every some years. So that means that the most important, this is the International Congress of Refrigeration that is organized every 4 years. And in this conference, they cover all the topics of the IIR, but there are other conferences that they are more thematic, covering different fields. So this is one is this is the Gustav Lorentzen Conference on Natural Refrigerants that is organized every 2 years. The Conference on Sustainability and the Cold Chain that also is every 2 years. The Conference on Thermophysical Properties and Transfer Process of Refrigerants, that this is every 4 years. So that means that there are all this conference of ammonia and carbon dioxide refrigeration technologies. So that means that they are covering the different fields, and also they are changing the hosting, the country and the organization that is hosting the conference. They are decided in the IIR with the different countries. They can present the candidature. So the next. So and now we can go to the heat pumps and the energy recovery. So that means that this is well, as you know, well, and Professor Multi has explained in the introduction, heat pumps and refrigeration system. This is from the thermodynamics point of view, this is same type of cycles. This is similar technology, but there are some differences important that we have to take into account. And this is that the purpose of the heat pumps, this is heating, and that of refrigeration, this is cooling. Yeah. So that means that the operating conditions of these two systems are different and can be really very much different. So, but also some of these systems can be used for heating and cooling simultaneously. Yeah. Or even in some moments can operate as for heating, and in other moments can operate as a cooling, that it happened with the heat pumps in buildings. Yeah. So for IIR, sorry, the last. So for IIR, that means that the heat pumps, this is only an application more, of the refrigeration systems. Yeah. And well, and as I mentioned before, there is a commission, that is covering this topic of the heat pumps and energy recovery. And all the commissions, they have that the rolling for 4 years plan that they cover, they schedule all the activities that they will be or they are scheduled for the 4 years. So that means that here I have just collected the activities that in the frame of the conferences that they were organized when the commission E2 was involved in the last 3 years. So that means that here you can see that, for example, there are the conferences on compressor and refrigerants. This is in Bratislava in Slovakia, or they have this conference on caloric cooling and application of caloric materials, Thermac, that it was in Maryland, in the United States. Or there are, so that means that all the, well, not all, but most of the conferences that I showed before, they are also very, our commission, it was really very involved in them, no? So that means that, but this is not the only type of conferences where the commissions are involved. In the next, you can see here what is the other conferences that they are organized by the other organizational entities, and the IR is participating. So that means that, for example, there are some very important conferences in the field of the heat pumps, and this is like the heat pump conference organized by the International Energy Agency. Here we have that it was organized in 2021 in Korea, or recently in May of 2023, it was organized in Chicago. So there are other conferences that also they are co-sponsored by IR, like the International Substation Heat Pump Conference, that like it was organized in Berlin in 2021. So that, or even one conference that is organized in my country, in Spain, that this is the Ibero-American Congress of Refrigeration Science and Technologies, that we celebrate every 2 years. So on, and just to mention the important note that the heat pump is having at this moment, is I can mention that in there is the China Heat Pump Conference, that it was organized for the first time in the 2022 in Hangzhou, China. And the second edition will be, this is scheduled for the next year, 2024. So the next, please. So the activity that the commission need to had in this part of the informatory note, really you can see here that this is really very important. So they were covering, I have put here that some informatory notes on air source heat pumps for heating and cooling. You see, this is, well, typically all the informatory notes are available in English and in French, but in some cases they are also translated and published in other languages. In this case, they are published in Chinese and Spanish. There are also one informatory note that I was particularly involved, and this is the high temperature heat pumps that it was published in October 2021. There are other covering the passive cooling, renewable energy today, geothermal heat pumps that is now in progress. So that means that this is a very this type of information is very attractive also for the developing, for the members of the commission. And we have a list, important for the continuing, producing this this informatory note for the next year. Well, other activities that we have done, and this is, for example, we organized in the frame of the World Refrigeration Day in 2021, one webinar on high temperature heat pumps, new career opportunities for decarbonization of the industrial sector, that also Professor Saravanan was participating, and many others from different countries. Or recently in the International Conference of Refrigeration in August, we organized a workshop that this is the use of hydrocarbon in refrigeration and heat pumps. And this workshop was organized in memory of two professors that they were really very active in this in the development of this topic. So the next, please. So here, this is some information regarding the 26th International Congress of Refrigeration that was celebrated in Paris recently. So here, well, I have collected some information. Well, you can see that it was a very important conference with more than 1,000 participants. There were also, well, many countries represented, around 100 technical sessions covering the different topics of the commissions. And well, and that is interesting is that these communications, these papers that they were presented orally in the different technical sessions, you can see there what is the distribution, no, with the topics of the different commissions, no? And there is interesting to see that this commission on heat pumps, no, they represented, this is more or less 24%, no, of the total papers presented. So that means that this is indicate, no, that this topic is now attracting, no, many researchers and many technologists, no. So, and maybe the next conference, well, this topic is now is interesting, no, for the community, no. So you know that the heat pumps, this is well known, no, that this is a key technology to decarbonize the heating sector, not only in buildings, that this is quite well known. This is also in industries. Yeah. So heat pumps, this is an efficient way, no, to produce the heating. So that means that this is well recognized. But in the last 2 years, no, we have in Europe, no, this the Ukrainian and the Russian war. So that means that this situation has created a very big problem in terms of the energy in Europe, but also in the world. And this is that the prices, no, the oil and the gas prices, they have increased a lot. So that means that this situation has accelerated, no, the demand for heat pumps and has put in pressure on the suppliers, the heat pump suppliers, manufacturers, users, and all the actors, no? So that means that, and this is only to give some figures, no? Related with the role of the heat pumps and what is expected for the next years, no? According to the International Energy Agency, heat pumps has to provide 1/5 of the world's heating needs by the end of this decade. So that means that the global installation of heat pumps has to increase from 180 million in 2020 to approximately 600 million in 2030. So that means that the installation rate of heat pumps in buildings, not that this is, we say that this is the common, no, application, has to increase from 1.5 million per month at present to approximately 5 million in 2030. So that means this can give the idea, no, of what is the situation, no, for the current situation for the heat pumps and what is expected. So the next, please. So that means that the potential heat pumping application, they cover all a wide range of temperatures, levels, heating demands. That this is the space heating, that this is quite well known, domestic hot water production, but also process heating, simultaneous heating and cooling, solar assisted heating, thermal energy storage. So that means that there are a lot of fields where the heat pumps can be applied. But this is not so simple. No, there are some challenges that they require. No, some innovation, some R&D for the heat pumps to deliver heat at the high temperatures, operating in some cases with the large temperature lift that is happening in the industrial application, or even for the integrate, no, with industrial process. So that means that there are many fields that they show that the R&D and the innovation, this is required. So that means that, well, here, this is, I think this is just to finish. Here, this is only what was the activities, no, in the field of the heat pumps and energy recovery that they were happened, no, in the frame of this International Conference on Refrigeration, the keynote lectures, the full papers, but also interesting is what is the technical topics, no, for the technical sessions. And there you can see that they were most of the papers, no, presented in this technical sessions are referring, no, to the refrigerants, particular natural refrigerants like CO2, that they were around 14 papers. So that means that, but also the other refrigerants and the refrigerant mixtures, particularly also with hydrocarbons. But another topic that it was attracting, no, many interest, no, for the communication. This is for the high temperature heat pumps and the last temperature lift heat pumps. No, that this it was really a very important topic with 3 sessions, but also there were some workshops that they were specifically on this topic. Of course, the heat recovery, this is also a very interesting topic. So the next, please. So that means that here, this is, yes, I recover, no, what is the R&D trends, no, that they were detected in this conference. Also for the industrial application, this is important, no, that some of the in the industry, no, that it is frequent, no, they use the steam. So that means that in some cases the steam boilers, well, cannot be directly, no, replaced, no, but the heat pumps. So that means that maybe the process has to be redesigned, no. But this is an interesting topic. So maybe the next, well, in the next, that this is just to finish. I recover some of the. Can you please? Yes. So I recover some of the papers, no, that I consider that they can show, no, what the well, these trends, no. And one, for example, this is that it was presented by or developed, no, in the Norwegian University of Science and Technology, and this is about the performance of the ammonia water absorption compression high temperature heat pump for hot water and steam production, no. So that means that this is interesting, that the production of this heat can be in this range of 100-150 degrees, and also has some innovative part, this type of heat pumps that they are with ammonia water and combining this absorption and compression technologies. So the next, please. So an interesting also paper that it was covering, no, or showing, no, the different demonstration projects of high temperature heat pumps integrated with industrial process, that they were, well, this is, they said, the real life conditions. So that means that they were covering some, the powers from 50 kilowatts to 1.7 megawatts, and the supply temperature was between 120 and 184 degrees. So that means that they show, no, that this is a technology, that this is, well, in this field, no, the high temperature, there are, no, some technology that is there, and also there are cases where illustrate the interest, no, and how is the methodology to integrate in a process. So, well, there are other interesting papers that, for example, this is one topic that this is really very important, and this is the compressor, no? So here there are one paper that this is an experimental design of also an ammonia water absorption compression heat pump for heat supply at temperatures up to 200 degrees. Yeah, so that means that this is a new type of compressor, that this is the oil-free. So that means that it is a very interesting paper. Well, so this is all. So maybe this is just, well, you can go to the last one. Next, please. Yeah. So here I try just to summarize, no, that the role of the IIR, no, that this is an independent intergovernmental science and technology-based organization promoting, no, all the knowledge of refrigeration and these other technologies associated, the activities that the Commission E2 on heat pumps and energy recovery that they are doing in the frame of organizing or participating, no, in different type of conferences and conducting the working groups, informatory notes. So that means that this is, well, maybe the next, please. Yeah. So, well, no, before, well, this is just to show, no, what is the role of the current interest, no, on the heat pumps. That this is an important technology that now has well, is showing what is the interest that we have in this moment, that we are decarbonizing different sectors, like building and industries. Yeah, and well, this is only remember that there are some work to be done, in demonstration, innovation. So that means that this is a good field for companies and many students, professors. So that means that this is for the research and innovation. This is a very attractive field. So this is all. And
Thank you.
Thanks for your presentation, for your attention.
Thank you, Alberto. It's very interesting, and then I'm sure that people came to know what are the important areas of heat pumps. And I request Professor Sukumar Devata to hand over a small memento to you. Otherwise, okay, thank you again. Thank you, Professor Devata. I think that the next one is online, and the speaker is already waiting. So the next one is on industrial heat pumps for heating and cooling applications. This is by Dr. Andy Pearson, Group Managing Director of Star Refrigeration, Glasgow. I think he is online. Yeah, can you get him on?
Talk number 242, Industrial Heat Pumps for Heating and Cooling Applications, Dr. Andy Pearson, Group Managing Director, Star Refrigeration, UK. Dr. Andy Pearson, an ASHRAE Fellow, is the Group Managing Director of Star Refrigeration, UK. Established in 1970, Star Refrigeration leads the way in natural refrigeration and heating technology. Working closely with its customers, the company strives to offer a comprehensive range of cost-effective, eco-friendly, socially responsible heating and cooling solutions to suit various business needs. He is experienced in the design and installation of industrial heat pumps. We welcome you, sir.
Thank you very much. Good afternoon, everybody in Chennai. I hope that you can hear me. I'm calling you from Scotland. Greetings from everyone in Scotland. I'm sorry I can't be with you, but I'm delighted that the technology allows me to participate in your conference. And I congratulate the organizers for an excellent series of presentations throughout the Refcold' conference, particularly to the team at ASHRAE who have pulled this together. Well done. It's really fantastic. So I'm talking a little bit about the general concept of industrial heat pumps, looking at heating and cooling applications. And it's very good that this follows from Professor Corona's overview of what's happening, because I agree with him. It's a very active field at the moment. It's a really good time to be an engineer in the refrigeration business. So I want to set some basic ground rules. First of all, this is a maybe now not typical refrigeration system. This is the original Jacob Perkins system built in 1834, but it shares features with every refrigeration and heat pump system using vapor compression, which are that heat is brought in surroundings at lower temperature and is extracted and rejected at a higher temperature. And whether you're interested in the cooling side or the heating side, it's the same system. And in order to achieve that lift, you need to do some work in the compressor of the system. And for this presentation, I'm going to try and discipline myself to use the term heat elevator instead of heat pump, because a lot of people, particularly non-technical people, don't understand the term heat pump. It's a bit confusing for them. And when you say to them, you're lifting heat from a lower level to a higher level, like an elevator in a building lifting people, they kind of get it. So I'll try to talk about a heat elevator, and coefficient of performance causes problems as well. So I tend to refer to this as the heating advantage in the same way as with a gas boiler. you might have a heating advantage of 80%, which means that 80% of the calorific value of the fuel is delivered as heat. As Professor Coronas pointed out, with a heat pump, you can get a heat advantage that is greater than 100%. And again, this tends to confuse people unless they understand what's being talked about. So heat elevator, heating advantage are the terms that I will try to use in the presentation. And of course, in refrigeration world, we talk about the COP of refrigeration. It's the heat that's taken out of the surroundings divided by the work input to the compressor. So the blue bit divided by the yellow bit, just to keep it simple. And for heat pumps, the heating advantage is defined in a very similar way, except that it's the heat delivered at the output divided by the work input. So the red bit divided by the yellow bit. And I'll come back and talk a little bit more about these in a moment, but I want to share some philosophy with you first. If you're down at the beach and you're building a sandcastle, you will be very, very interested in the size and shape and form and appearance of the pile of sand that you're working on. And here's a beautiful example of a very nice sandcastle. The shape and the texture and the form are really, really important. But you don't actually really mind, you don't care about where the sand came from. There will be a hole in the beach somewhere else, and it's really not important. You're focused on the form of the output. However, if you're working like this scenario, you're much more interested in the hole in the ground. You're interested in the length, in the width, and particularly in the depth of the hole, and you don't really care about the pile of sand that you've taken out of the hole. It really doesn't matter. And the sandcastle is a bit like the heat end of a heat pump, and the hole in the ground is a bit like the cold end of a refrigeration system. So when we talk about coefficient of performance for refrigeration and heat advantage for heat pumps, we can obviously see that the heat delivered in the heat pump is the refrigerating effect plus the work input. So the heat advantage is the refrigeration COP plus 1 in simple terms. When you're doing simultaneous heating and cooling, it's very tempting to add together COPR and COPH. And you quite often see this in presentations. You may even see it in some presentations later today. And this gives what people call a total coefficient of performance. But actually, this doesn't really make sense because what you're doing is adding together 2 times the refrigerating effect plus the work divided by the work. But the heat being extracted is moving in one direction. The heat being transmitted is moving in the opposite direction as far as the system is concerned. So adding them together is not really logical. And in particular, this COP total, as people call it, is a very unhelpful number. The COP of refrigeration helps you to analyze the system performance and think about capital investment. Particularly the heat advantage of the heat pump does the same. You can decide, is it worth spending money on this capital plant in order to get an advantage? When you add the 2 together, you no longer have that ability because it just doesn't make sense. And in my mind, it is the equivalent of adding graves and sandcastles. It's just nonsense. It really doesn't work. So what you have to do, unfortunately, if you're thinking about simultaneous heating and cooling, you need to think about the incremental heat advantage, what I've called here as COPHI. And the incremental heat advantage is the heat delivered, but divided by the difference in work input between the work you have to do to deliver the heat minus the work that you would have had to do to deliver the refrigeration anyway. In other words, it's only the additional. So if you're delivering 100 kilowatts with a heat pump that's consuming 50 kilowatts, your heat advantage in simple terms would be 2. But if the refrigerating system would have required a heat input, a work input of 40 kilowatts anyway, then the increment is only 10. So actually your incremental heat advantage is 10, not 2. And therefore you would correctly make a capital investment when you consider the incremental heat advantage that you might have been dissuaded from if you had considered just the heating COP. And if you were to take those 2, heating COP and cooling COP, and added them together to get a total, it would not give you the true picture either. Your cooling COP, refrigeration COP would have been 2.5, and your heating COP therefore would have been 3.5. So the total COP was only 6, but actually the increment is 10. So it's a more powerful argument for justifying the capital expense if you do the more difficult calculation and you do it correctly. So, of course, you then need to think about, well, what's the residual refrigeration COP? And of course, it's the heat extracted to give refrigeration, but only divided by the work input for that refrigeration effect, not the work input for the heat pump. So still 2.5 in terms of the example that I gave. The more difficult question to consider when you look at this in terms of the cooling plus the work input, the more difficult question is, what would a residual refrigeration COP look like, an incremental COP? And this is actually extremely difficult. I will come on to that in a moment when we look at some example calculations. So heat pumps for industrial applications, as has already been said, they're used in lots of different places, and the different places will require different sizes of equipment, and they operate at different temperature levels. So I picked 3 typical examples just as an illustration. Again, I would say the important thing is when you're doing your own calculations to justify your own capital investment, you have to use your own numbers. Don't be tempted to use some of the numbers that I'm presenting. Be accurate in what you're doing. So if your heat pump is delivering wash water to a food factory, for example, it might need to be delivered at a temperature between 50 and 70 degrees C, and it may have a capacity of hundreds of kilowatts for the system. So you can see on the graph of temperature against size of system heat capacity, it's down in the bottom left-hand corner. If it's a powder drying process, and I know some of the later speakers will talk about powder drying, it may need to be at a higher temperature, and it may need to be a physically bigger system. So maybe around about 100 degrees and perhaps 1,000 kilowatts. And if it's a steam raising plant, it will need to be at even higher temperature and potentially will be even bigger. So these 3 different systems have very different characteristics, and they require very specific analysis. So I've graphed this in terms of the temperature lift, thinking about the source temperature and the delivery temperature, and looking at the heat advantage for these systems. And the contours on this graph are of different source temperatures. The bottom line here is the 0 degree source, and the top line, the pale blue line, is 100 degree source. And you can see that the higher the source temperature for a given delivery temperature, the better the heat advantage will be. But the higher the delivery temperature for a given source, the lower the heat advantage will be. And if we think about our 3 archetypal heat elevator systems, wash water would occupy this area of the graph, and powder drying this area, and steam raising this area. So if you're looking at steam raising and you want to calculate a heat advantage, really you want the source to be as high a temperature as possible. You want to be recovering heat from the industrial process, not using ambient heat if it's just a steam raising heat elevator. If it's combined heating and cooling, then again, we'll come to that in a moment, it gets more complicated. So if we look in the Indian context, I tried to get some figures on cost of fuel. An industrial tariff for electricity might range per kilowatt hour from 10 to 20 rupees, and natural gas seems to be, for a kilowatt hour of calorific value, about 2.5. So this would give you a spark ratio, the ratio of electrical cost divided by gas cost, ranging from 4 to 8. And in other words, you would need a heat advantage that exceeded that spark ratio if you wanted your heat elevator system to be financially viable, just purely in terms of operating cost. So that blots out the bottom end of the chart. If you're working with such a low source temperature that you cannot achieve sufficient heat advantage, then it's not financially viable. The temperature lift is too high. If you're considering a comparison with a coal-fired system, it's even worse. Costs of coal seem to be round about 1.5 rupees per kilowatt hour of energy input. And this gives what is known as a dark ratio. Compared with that industrial electrical tariff, the ratio would be somewhere between 7 to 13. So if we take a midpoint of about 10, it means if your heating system is coal-fired, you would need a heat advantage that exceeded 10 to make it financially viable, just from a fuel efficiency, fuel cost point of view. Of course, there are other reasons why you would want to move away from coal. Perhaps a carbon tax might be applied as well, and that would skew the costs. Or maybe there's a concern about particulate emissions from the combustion process. And again, there would be an imperative to move away. So there are other reasons to justify the heat elevator system. But if you're just purely looking at operating cost, temperature lift affecting the heat advantage is a big challenge. So I took the same information, plotted the contours differently using the source temperature along the x-axis and plotting contours of the delivery temperature. And again, you can see how the gas-fired limits the application. And if we were to look at coal-fired, it limits it even more. But sources of heat might be suitable for wash water, but not suitable for powder drying or steam raising. So it gets complicated. Now, I would like to present a series of 4 case studies on different aspects of the calculations that you would need to do. And again, I would emphasize, these are not real life examples. You need to use your own data to do the calculation. But the first point that I want to make in the case studies is that the small details are really important. If you were considering a system that nominally delivered 10,000 kilowatts of heat and had a shaft power of 2,300 kilowatts on the compressor, then you might say, oh, my heat advantage is my heat delivery divided by the shaft power, 10,000 divided by 2,300. I've got a heat advantage of 4.35. However, the heat delivered is actually 2,300 plus 7,500, the refrigerating effect. Therefore, that brief calculation is wrong. It's 9,800, and the electricity that you're using is not the shaft power of 2,300, it's the electrical input, which might be 200 kilowatts higher, 2,500. So your heat advantage isn't 4.35, and even in this simple example, it would be 3.92. But it gets even more complicated, because if you make allowance for heat losses from the system, not all the heat extracted can be delivered to the process, and you have perhaps a motor efficiency to bear in mind and an inverter efficiency. You've got an ancillary load with, for example, the oil pump and the compressor, so it's not just the shaft power. You need to consider these ancillaries. And to get the heat from the source to the heat elevator, you need to do some pumping as well. So you'll have inlet pumps, for example. Once you do all of that, and you put in some realistic numbers, you find that the heat advantage is actually 3.59. Now, 4.35 sounded really good. 3.59 is a little bit less attractive. But in terms of many countries around the world, that's still a very respectable heat advantage that would give you a financial justification for doing this, even although it's rather lower. So you can see that by paying attention to the small details, the heat advantage is about 20% less than the simple assessment would suggest. And if you were doing a financial calculation on is it worth spending the money, I think it's important to be accurate and to have the correct information. So the second case study that I'd like to share is looking at incremental heating. This photograph is of an installation we did in a food factory where the chilling effect is being used to chill glycol for the cooling processes in the factory. And 2 of the 4 compressor units are operating at a higher discharge temperature to deliver hot water for wash down and for process purposes, the hot water side being at about 60 degrees. So as I mentioned earlier, in this case, it's important to calculate the incremental heat advantage, which is the heat delivered divided by the difference between the work required purely for refrigerating and the work required for heating. If we were delivering, say, 560 kilowatts of heat with a work input to the heat pump system of 160 kilowatts, that would be a refrigerating effect of 400 kilowatts. Now, the total cooling effect required in this system is 500 kilowatts. And when we run just the cooling system, we have a COP of a work input of 1.25 and a refrigerating effect of 500 kilowatts. So we would have a COP of 4. But when we boost the discharge temperature, we need more work input. So it's 160, not 125. But also we get less cooling effect. So it's 400 instead of 500 in this example. So I would actually be taking 560 divided by 35. It looks as if my incremental heat advantage is 16. That sounds absolutely fantastic in comparison with my basic heat advantage, which would have been 5 in this instance. So this is really good. Unfortunately, as in the previous case study, it's wrong It's not sufficiently detailed because in this case, I need 500 kilowatts of cooling. So if I reduce the capacity by doing my incremental heat advantage and running simultaneous heating and cooling, I'm going to run some further chilling capacity, again, with a COP of 4 to deliver that extra 100 kilowatts of cooling. So 100 kilowatts of cooling with a COP of 4 means I'll need to put in an extra 25 kilowatts into another chiller to give me my 500. And therefore, the correct calculation would be 560 kilowatts of heat delivered, but 160 plus 25, 185 minus 125, so 40 kilowatts incremental, giving me an incremental heat advantage of 9.33. Now, this is still good. It's not at all inappropriate, but you can see that accounting for the extra work input for the additional chilling, which is a necessary part of the total calculation, has dropped my heat advantage by about 42%, less than the simple assessment would have suggested. A heat advantage, an incremental heat advantage of 9.33 is still exceptionally good and is worth doing. But if you want to retain credibility with the financial managers in the company, I think if you offered them an advantage of 16 and they said, wait a minute, it's only 9.33, your credibility would be somewhat diminished. So again, small details matter. And in doing the incremental heating calculation, it can very quickly get a bit complicated. So a third case study, in this case, looking at, again, something that was mentioned by Professor Cornas, the simultaneous heating and cooling, in this case, taking an existing large cooling system, a chilled water system, and adding a water source, water heating heat pump, using the chilling system as the source for the heat pump. But the key thing to bear in mind here is that there is a time discrimination between the time that the cooling is done for the building and the time that the heating is delivered. So we can't just use the kilowatt hours extracted, sorry, the kilowatts extracted and the kilowatt work input at any instant in time, because the cooling and the heating are not happening simultaneously. So again, there's a degree of complexity that needs to be borne in mind in doing the calculation. So to give a worked example, we need to think about the heat delivered and the work done and the cooling extracted over a defined time period. And it's quite convenient to take 24 hours, a full day as the time period. So we think about the work input in kilowatt hours over the day, the cooling effect in kilowatt hours over the day, and the heat delivered, again, kilowatt hours over the day. So for this example, the difference in work is not happening instantaneously. We run the heat pump and we cool down the chilled water circuit using it like a thermal store. And then when the chillers are required to run, they don't have to run quite as much or quite as heavily loaded. And therefore the saving, the increment in refrigerating effect is happening at a different time. So I'll put some numbers against that. Let's imagine a system that requires to do 30,000 kilowatt hours of cooling over the course of 24 hours and has a chiller COP of 5, water-cooled chillers in the basement of a big hotel, for example. So the refrigerating effect is 30,000 kilowatt hours. The work input to the chillers over the day will be 6,000 kilowatt hours. If I were looking at a heat pump that's delivering 1,500 kilowatt hours over the day and a work input of 250 kilowatt hours, my increment for not doing that 1,500 kilowatt hours, 1,250 kilowatt hours of cooling that is being done by the heat pump would also require 250 kilowatt hours. So you can see that my incremental heat advantage would appear to be infinite because the additional work done by the heat pump is exactly matched by the reduction in work required by the chillers over the course of the day, because we're making the chilled water loop a bit colder by running the heat pump, and therefore we can back off on the chillers. This sounds like a fantastic proposition, but there's a bit of a hitch to it because we're going to have to spend more money to buy the heat pump compared to just buying a gas boiler. And the incremental fuel efficiency that we need to consider is the electricity used in comparison to the saving in gas in the gas boiler. So put a few more numbers against it. We want to calculate a payback. It's the cost increment divided by the operating increment. In other words, the capital cost of the heat pump instead of the boiler divided by the fuel use for the boiler. So if the $1,000 and the boiler cost $10,000, the increment would be 40,000. And to deliver 1,500 kilowatt hours a day of heat might require gas use of 1,875 kilowatt hours per day as the increment or the saving against the gas boiler. Now, gas historically has been exceptionally cheap in many parts of the world. If we were to use a figure of 2.5 cents per kilowatt hour for gas, this payback would be ridiculously long, 23 years. More recently, because of global events, gas prices have rocketed. They've escalated massively, and therefore maybe 25 cents per kilowatt hour would be more appropriate. And in that case, the payback would be 2.5 years for installing this water source heat pump in the basement. So perhaps a proposition that is more attractive now than it would have been originally. And the same kind of analysis would apply to combined heating and cooling in a food factory, but you need to do the complex calculation, not just add the refrigeration COP and the heating COP. And then for the fourth example, I picked a case study not based on food factories at all, but actually looking at an ice rink just for a bit of variety. And that's because this is an experience that I had early in my career. So it's a very instructive story. It's very good teaching points come out of it. So the story is that there was a town council who had a department that operated a swimming pool and another department of the council, completely separate part of the overall leisure facilities, that operated an ice rink. And the ice rink was in one building and the swimming pool was in a different building across the street, but the ice rink equipment was in the basement of the swimming pool and the brine pipes to the ice rink ran in a trench underneath the road. So we have two departments sharing a common facility in terms of the mechanical equipment to heat the swimming pool and the mechanical equipment to cool down the ice rink. And they decided that it would be a really good idea to get together and add a heat recovery condenser to the ice rink chiller so that they could provide heat to the swimming pool. And both departments agreed that this was a worthy thing to do. And they agreed in principle that the ice rink department would monitor how much heat they supplied to the swimming pool and would send them a bill at the end of every month for the amount of heat, but it would be a much lower rate than the cost of running their boilers to heat the swimming pool. So the bill would come in at very favorable rates. The swimming pool would save money and the ice rink would get a bit of revenue to pay back the capital cost of adding this modification to their chiller. And the quantity of heat that the swimming pool people specified that they needed was far, far more than the ice rink could possibly provide. It was a factor of 10 higher than the heat rejected by the ice rink in a typical day. So we looked at this and we said, well, they need so much heat that everything we can give them is beneficial. We'll just design a system that can deliver as much heat as possible. But this was wrong. This was a mistake in the specification. Unfortunately, there was no way to turn off the heat recovery without causing operational problems to the ice rink. You could just have shut the inlet valve to the additional new condenser, but it would have tended to fill up with liquid in that case, and the chiller wouldn't have worked properly. You could have turned off the water flowing to the additional condenser, but then the water that was in the condenser would get very hot, and when you brought it back online, there would be a flood of very hot water around the swimming pool circuit, which would be a bad thing. So it actually proved to be technically quite difficult. We did manage something in the end, but this was also a mistake. Designing a system that had no way of turning it off proved to be problematic. And the consequence was that the swimming pool got very warm, and it was beautiful. You know, it was supposed to be 27 degrees C, and it was regularly at 30 degrees C. And the council representative phoned me up and said, we've got a problem because the pool's at 30 degrees. And I said, well, is that not a good thing? You know, it's nice for the swimmers. And he said, well, the mother and toddler group that come in at lunchtime absolutely love it. They think it's fantastic. But the competitive swimmers that come in at 6 o'clock in the morning to do their training are just about dying. They're just killing themselves. So we need to solve this problem. The pool is too warm. And the consequence was that the pool department said, well, we never wanted the heat, so we're not going to pay for it. So the lesson learned is that recovering heat, having combined cooling and heating, is only valuable if somebody actually wants the heat and if they're willing to pay for it. So in doing all of these fancy complex calculations that I showed you previously, you need to bear in mind that this is only of value if somebody actually wants the cooling or somebody actually wants the heating. It needs to be a fully integrated system. And we actually find this is one of the biggest hurdles to persuading customers to do combined heating and cooling, because they say, well, I'm running a sausage factory or I'm running a cold store. I don't want to get into the business of supplying cooling or supplying heat. I just want to keep things focused on my own needs. So there's a hurdle to be overcome there. And it requires good cooperation between all parties and accurate information, as was not the case with this ice rink example. So there's 4 case studies that hopefully will help inform doing appropriate, suitable calculations on the justification for heating systems, and particularly for combined heating and cooling systems. So we can draw some conclusions. Firstly, to say heat pump economics need to be a good fit combination of both a low capital cost and a high efficiency. And these are sometimes seen as things that fight against each other. You can have it cheap or you can have it efficient, but you can't have both. So the trick is to try and strike the right balance. Don't go for the cheapest possible system, but also don't go for the absolute most efficient system. And calculating the benefit correctly is absolutely essential to justifying the investment. I've illustrated just a few of the pitfalls in doing these calculations, but you will find your own, undoubtedly. There are very many. It needs a good understanding of the process because it's not always easy. So the lessons learned from the case studies, small details are important. Incremental heating needs to consider the whole system cost, and the payback is very sensitive to the cost of fuel that you're no longer using. And that in itself can be very difficult to predict these days. So your financial calculation is going to be subject to be a large amount of variability. And the tendency for the financial people will be to take the safe option and be very pessimistic. And that again is a serious impediment to the implementing of systems that would be very useful and perfectly good. So there's a challenge to overcome there. Your calculation needs to be robust. It needs to be believable if you want people to put forward the finance that you need. And as I mentioned earlier, the heat recovered is only valuable if someone's willing to pay for it. So in conclusion, don't be tempted to add graves and sandcastles together because it just doesn't make any sense. So I will stop sharing at this point, and I hope we've got a little bit of time for questions if there are any.
Thank you.
Hello.
Thank you, Dr. Pearson. It was a very nice and interesting talk. We learned a lot. I don't think that we have a lot of time for these things. I think one of your friends wants to ask you a question.
No.
Hello, Sukumar. Nice to see you.
Yeah, nice. I just wanted to say thank you very much for accepting our invitation and then delivering a talk. I must add that in spite of your Glaswegian accent, people here still could understand you. Thank you very much.
Well, that's very kind of you to say so. Thank you.
It was very clear and very interesting. Thank you very much, Dr. Pearson, for your nice talk. And now we can take the next talk. Thank you.
Okay, thank you.
Yeah, now we have the next talk by Professor Armin Hafner from NTNU, Trondheim, Norway. It's on carbon dioxide heat pumps for process heating and cooling.
Talk 243. CO2 heat pumps for process heating and cooling. Professor Armin Hafner, NTNU, Norwegian University of Science and Technology, Norway. Professor Armin Hafner is a professor of Refrigeration Technology at the Norwegian University of Science and Technology, Norway. Over the past 2 decades, he has been working at SINTEF with research topics related to CO2 refrigeration technology for various applications. His focus is on refrigeration and heat pump technology in general, and particularly in CO2 technology for multiple applications such as supermarkets, industrial heat pumps, and transport refrigeration. His work involves system design for refrigeration, air conditioning, heat pumps, and working fluids, especially natural working fluids. We welcome you, sir.
And since the microphone is working now, I can lower my voice. Okay, we are already very far into the presentation, so let's start from this one. Welcome, everybody. Thanks for coming after lunch. I hope I can make it on time to the coffee break. Trondheim is there on the dot, so we are a bit more north than you. You're very more close to the equator, and we appreciate the heat all year long. So, but in our case, we need heat pumps. As Andy said, and you see, he's even further south than us, but even in that place, we need heat pumps. Just a few words about Trondheim. Those who are not been able to visit us, we are the technical capital of Norway, and there are a lot of technical students in our area, and welcome to visit Trondheim and our university. And this is how it looks like these days. But what is important nowadays? The clean energy is really something we need for a peaceful, sustainable society. That's the largest challenge we have nowadays. And the clean energy is required to visit Trondheim and our university. What happened? No problem. But food, housing, and transportation, it's all to have a good life on this planet, and it's you. And if you point to somebody else, there are 3 fingers pointing to you. So that's always also important. It's also me, it's not only you. But that's what we are thinking together today. So I will talk a very short, brief history on CO2 refrigeration, some application examples, and a summary at the end of the day. So what were the drivers? Where does all mechanical refrigeration start? Well, it was starting with artificial ice production. To do this, we did this in Norway. It was a very big business. Even the ice was cut in Norway, brought to Great Britain, and they brought it all the way here to have the Scotch on the rocks. So the rocks came from Norway, the Scotch came from where Andy comes from, and it came all the way here. However, and you see, this was big business for Norway. We exported a lot of ice, same amount in volume like we do fish, salmon today, big business. But there was also CO2 refrigeration already by that time. You see, in the US, they did these blocks of ice artificially by CO2 systems more than 100 years ago. So the development was more or less because of the beer. Carl von Linde, he developed mechanical refrigeration to make the Germans able to produce beer all year long. That was the start of mechanical refrigeration. He made a great fortune on 750 units he sold in a short period. After that, he went back to the university and developed the cryogenic sector. That was before. First, he sold all his ammonia systems, and then he came back to cryo. So, transport of meat, but we have many vegetarians here, we skip that. But you see, here is how they transported all the meat from South America in these large ships, and you see on the upper left the CO2 system, and down is the meat. This was typically done by J.E. Hall compressors, and all these big manufacturers had this kind of compressors. So it has been there before. But in the meantime, we saw the CFC, HCFCs, they came on in. We had the Montreal Protocol, and luckily, so there is a change, there is a kind of knowledge about this kind of fluids. We need to do a change. We have the F-gas regulation now, and we are looking into a new phase. However, the question is, do we really need the F-gases? That's the big question. 10, 15 years ago, not all of us were aware of all these alternatives, but now we have the alternative, and that's why. And what is the problem with the F-gas? Those of you who have not been here yesterday, The challenge is, of course, we do not do CFCs anymore. There's still a lot in the field, in the area. However, we have global warming and we have PFAS. These forever chemicals, that is we can do a difference. We do not need to implement these systems now, creating the problem for our kids. We know better now, and we can do a difference. And you will not lose the job. Nobody will lose the job. We create more jobs. So this is the way to go. This is why we have these European environmental agencies making this proposal for the restriction. It's not to kill our business. It's to remind us our responsibility. And this is up to us to do this now or in 5 years, or as I said later this morning, if you don't do this, you have to come back and clean up later. Why should we clean up later? We do better now. So the natural working fluids, they are the future, and it prevents to invest in midterm things which you regret in 5 years. Why didn't I do R290 system straight? Why didn't I do CO2 in 2023? Rethink about your investment when you develop new systems. Are they intermediate or are there solutions for real cooling? These are the fluids we are talking mainly about. I will focus on the first one to look into hot water heat pumps. I don't have a picture, but in Japan, they have 6 million hot water heat pumps for the houses to make the hot water in Japanese homes. And we see a lot of commercial refrigeration and some heat pump chillers, which I want to share you. So, but let's go a little bit to the basics. What is the difference between the CO2 as a working fluid and the conventional low pressure working fluid? Well, the advantage is we have a high refrigerant density. This means the compressor part of the compressor is very small. Swept volume is very small, but most of all, the compressor lines, the lines towards the system are relatively small compared to traditional fluids, meaning we can cope with the high pressure. The weight per meter is less compared to an existing system. And as you all know, weight is money. So it doesn't need to be more expensive because the weight per meter is less. We have a high compression efficiency, which due to the low pressure ratio, it's not the absolute pressure which gives the efficiency, it's the pressure ratio which counts. And we have a high heat transfer and a low specific pressure drop. That's a very good point. However, as you can see on the figure on the left, we have an increase in heat rejection loss. Of course, if we don't utilize the heat, this is negative. On the other side, if you want to produce boiler feed water, hot water to a very high temperature lift, this is the advantage. The other disadvantage is that we have a very high throttling loss due to the properties. Again, if we turn the challenge to an opportunity, if we utilize some of the expansion work, this is an advantage, an opportunity, I would call it. So let's have a look into some of these architectures, which I believe fit very well to India, to your customers in the refrigeration, in the food chain sector. Look at this. You can apply evaporating as a secondary fluid, CO2. Keep your ammonia system, take out the ammonia loop from the process part, send CO2 to your process, into the factory where you have the valuable food. Whenever there's a small leak or a leak, if there's a CO2 leak, the food will not be lost. People can escape. But if you have a leak with ammonia, you have a challenge with some fish or whatever. So that could be one solution. And this can be oil-free. So then there is no mess. If you do an indirect system with glycol or water, if that is contaminated, you have the same problem. CO2 will evaporate. There will be no mess afterwards. You just need to find the leak. You can have much smaller pipe dimension, and the pump work is, compared to glycol or other fluids, negligible. It's a bit more complicated. Expensive, I'm not sure. And then don't forget the cold finger unit. In case of standstill, Otherwise, you may lose the CO2 charge. So this small R290 system keeps the temperature low in the tank in the off season if you don't ventilate your CO2 system. But as Professor Pramod said yesterday, remember, 1 kilo CO2 is 3 rupee. So it's not a big issue on that part. There is an example of such a system. Maikawa does this in a large number of units every year. And look, the charge reduction is a critical thing. 1/38 less charge compared to existing another similar system. That is something very important, because in some areas you get challenged on too much ammonia charge in a well dense populated area. And this is one solution to do this. 1/38. We can also do a cascade system. We can go in with a CO2 compressor and go down in evaporating temperature. And that's a big advantage. So in the high stage of the cascade system, we use ammonia. We keep the ammonia as it is there, but we implement this cascade heat exchanger and utilizes a low temperature compressor. We can have a good energy efficiency and so on. I will just show you some example of this commercial product available. This can easily also be made in India, because you are all manufacturing all of these components. You don't need to add 10% import tax. You can build it here. Another system would be, or further improvement of this system. Look, you take the CO2 receiver, which is condensing the CO2 back with the ammonia system, and you pump also that CO2 towards your factory. Then you can do the chilling of the factory with CO2 at 0 degree, while you do the freezing at -50 with the low stage compressor. In that case, you can even avoid the freon chillers cooling down the production facility. So we don't need that one. All can be done by the centralized ammonia system. The little bit disadvantage is, of course, the CO2 loops rely on that ammonia system, because if the ammonia system stops, also the CO2 system cannot work. But with some redundancy on the ammonia system, I think this is a good option. And this can prolong the life or installation of ammonia systems for the next century, because we can reduce the charge and we can add this CO2 on the bottom side and do a lot of good installations with this. Very compact, very energy efficient. You can look at this. Okay, next is, if it comes. Yeah, and here we can go down to -50, -53. And that is something your customer will appreciate. If they have a big catch and they need to have a high pull through, they go down in temperature, otherwise they keep it at a little bit higher level. This is an example where we see this. Some of our friends have visited this factory, which was lately opened in Norway, where they do exactly like this. There is no water circulation in the process. They circulate CO2 in the whole chicken slaughtery at -5 and at -40 degree. So this is the machine room where you see some big ammonia screw compressors and some low stage CO2 compressors, piston compressors. And they use in this plant 29 cubic meter of CO2 at -7 and 8 cubic meter of CO2 at -40. Operating since 2 years, and they're very happy. What we also can do, we can do, of course, 2-stage compression systems to produce water on the hot side and very cold on the other side. This can be also improved by ejector systems and so on to do the work recovery at expansion to further boost the COP. An example of how to produce premium fish on such a small trawler, they converted from R22 to CO2 in the same place, in the same location. Left side was R22, middle is CO2, and they could install more capacity because of the compactness of the CO2 system. And inside the trawler, it was faster on defrost, and the freezing time was also much faster. That was a good story. This is just to show you the principle of freezing on a fishing vessel with a 2-stage system, where the lower stage is at -50, close to -50. In Norway, we produce the fresh fish on board. Fresh fish means frozen on board right after the catch. And then we keep the cold chain. These are the typical equipment where we do in horizontal or vertical plate freezers, where the fish is immediately frozen after the catch. Another example, just to show you where CO2 is applied, that even at CERN in Switzerland, to cool down the detectors at the physical, detectors in the LEC, we use CO2. We don't need to go into the details. Just have a look at supermarket systems. Around nowadays, it's really 100,000 supermarket systems around the world are using CO2. We see some of the examples, some in the booth, they have some examples from Europe, show some brochures. Because the transport properties of CO2 are good, so it's easy to hook up many cabinets to the system, and to control the capacity is also relatively understood. And there are a lot of companies offering this kind of systems. There's a huge competition, and you know the end user are shop owners. And shop owners are not so much interested in energy saving, they're interested in money saving. And because of the CO2 system, they can save money. That's why they do it, because they can do heat recovery in many places. You need heat to maintain the temperature in the shop. That's why these systems are so popular, even in Japan. Nowadays, I showed this yesterday also, this system is now commissioned in Portugal. It shows a very simple system where we have the compressors on the right-hand side. We may do some heat recovery if we need, but we also utilize the ejector to do some expansion work recovery when there is expansion work available. In the winter time, when the outdoor temperature is low, the system is running below the critical pressure. It's running as a condensing unit. In that case, we send the liquid on the red line straight to the expansion devices in front of each evaporator. So it's not running transcritical at all. And in that case, the CO2 is at a higher efficiency. It's only in summer we are normally suffering, but in that case, the ejector is helping to boost the performance. That's why we believe that this simple system will be the next generation of supermarket systems around the world. Very simple. We also did a study with our Indy Plus team to look into a CO2 air conditioning for a supermarket, for example, typical case in Bangalore. Normally, you install a chiller. If you nowadays install a chiller, it has a secondary loop on the cold side. Glycol is circulated or water is circulated into the shop. Sensible heat is picking up the heat. You cool down that with your chiller, and you use a water loop towards your condensing towards the tower and reject the heat via the water. If you do DX cooling inside the shop and do gas cooling towards the outdoor, your energy efficiency is equal compared to a traditional chiller. So that is a good, interesting topic to look into further when we have the investors and taking all the advantage which just Andy showed us, how to justify this kind of investment. So we have to redo some of the calculations. That was a very good advice from Andy, how to do that. But with double indirect loops, we can really compete. This is an interesting thing for a hotel. For hotels in India, we also see a very nice perspective, and we don't sum up both COPs, but as long we have hotels in India, they need cooling and heating. And this is a no-brainer to do with a CO2 heat pump chiller, because you have water tanks, or you have a water tank on the hot side, which can be charged 24/7, and 24/7 you may have cooling demand in the hotel. And by doing a proper design on the tanks, which are not expensive, you can really provide cooling and heating. And the cooling will be kind of the benefit to the other chiller units, because probably the chilling demand is much higher than the hot water production. But this is case to case. In some of the hotels, they also do their own laundry and all this stuff. In that case, you may see even that it fits perfectly for the entire demand, cooling and heating. And we will see this later. This year, it will go into operation at Goa, and we will show you the results when we see this system in operation. But what we see in operation is this system. It's one of the first of its kind, as Professor Pramod said yesterday. Your Indian Navy is smart. They bought a CO2 chiller into a battleship, and they were so happy that it could be elevated down with the elevator instead of making a big hole on the side of the battleship. That investment, if they would have had another chiller, it would be much bigger. They would have open up the battleship and weld it back. That would have cost much more than using such compact units, bring them down with the elevator and put them in. And they're so happy with this. I promise you in a few years, they will have ordered many, many of these. Are you ready to build them? That's your question. And this is our latest one. This you will all be able to show in a very few weeks at the Akshaya Patra Foundation School Kitchen at the ISKCON Temple in Bangalore. It will be on the parking ground. There will be no restriction to look at it and see it in action. So you're all welcome to go there and have a look how this unit is able to produce all the hot water for the school kitchen. With this hot water heat pump, they will be able to double the rice cooking for that kitchen. The rice cooking was the bottleneck because they had to charge with cold water, use steam to start the cooking of this of the rice. Now they can add 85-degree water to the rice, and by this they can double the production in the kitchen without enlarging the pots. So most of all, it's very important, as Andy said, we need to have the right numbers and make a fair comparison, but the end user must be aware that only green painting on the refrigerant bottle is not the solution. We need to tell them what is inside, and we need to train our workers, our engineers, our consultants. If we understand what clean cooling and heating means, we will not make any problems for our kids, and we can clean up our sector within the next decade. It's the end user awareness, and it's up to you and me to tell everybody to be aware what decisions we are doing. And if you have a doubt, look in the material safety data sheet of these fluids, what they all mentioned there. You will be surprised. So it's not only the GWP, which is important, it's all the other stuff too. So have a look on these sheets before you advise your clients to use these kind of fluids. How can we do this? I guess the government and others, they should help the first movers with some loans to cover this maybe additional costs, because they will be easily paid back by the operating costs later. So in summary, food, we need food, and it's so essential for humankind. And we need a safe and a reliable refrigerant equipment, so we're not losing the food. And that's why I think in the food sector, CO2 will play a big role to make this workplace safe and keep this food. And safe at work is very important, because even in this country, you lack people with the knowledge doing this kind of implementations. And we cannot lose one of them. And the natural working fluids, even though some of them are flammable, they are safe because we know how to handle them. If you use one of these synthetic fluids, which is supposed to be mildly flammable, and they treat it in a unscaled, untrained way, you will have a disaster, a problem. So we need to train them anyhow. We need to train all of them, but then we need to inform also about give them the awareness. And I believe, and many of us, I think, that only the natural working fluids will survive towards 2050, but we can start tomorrow. You don't need to wait until 2032 to find out, okay, now we should move. Because if you want to export this product out of India, you need to comply with this, but also in India, why should you wait another 10 years to do something? So let's cooperate and do clean cooling. Thanks for your attention. And maybe we have time for a question. Let's hope. Thank you.
Thank you, Armin. I don't think that we have time for questions because there's a short break, but I request Professor Alberto Coronas to give a small memento to Armin.
Thank you.
Thank you. It is not lunch break. It is only, you can't have one more lunch, just a few minutes only. You can take rest for 5-10 minutes. Let us start again. Thank you again to all the speakers. We will come back in 10 minutes.
Yeah, ladies and gentlemen, we will assemble back for the next session at 2:45, 3:45, sorry. Just. Yes, yes.
Indie group photo. Yeah, take. Somebody will take. You give camera, somebody will take. Yes. So there are 4 more, no? There are 4 more.
By Dr. translate is now what happened at
No, this is by mistake, repeated, so we have to close this. So we have Siddharth Paranjpe, Rigwen, and Jayaprakash. Okay, 3 more. So we Hello. Hello, Dr. Siddharth, can you hear me? Dr. Siddharth,
Hey.
hello. Can you
Yeah.
hear me, please?
Hello, I can hear you. Can
Okay.
you hear me?
We're not able to take your voice.
Okay. Can you hear me now?
Just go back to the old ones. Hello, Dr. Siddharth, can you hear me?
Yes, I can hear you. Can you hear me?
Yes, that's right.
Okay, I
I
see.
can hear you too.
Okay.
Just give
Yeah,
us 2
okay.
minutes. We
Yeah.
are just having a small break, and please be online, and we should be starting
Yeah.
in the next 5 minutes, Dr. Siddharth.
Yeah, okay.
Okay, just less than 5 minutes from now.
Okay, that's fine.
Okay. Dr. Siddharth Paranjpe, are you online? Can you hear me?
Yes, I can hear you.
Okay.
Yeah.
So we are going to start the session. Dr. Srinivasamurthy is still outside because we had a late break, but
Okay.
still to be on time, we would like to start the session. So you can, you can play the video. Yeah.
Yeah, so can you see my screen now?
Yeah. We can see.
Okay. All right. Then I will start.
Dr. Siddharth, please enable
Yeah.
your video, please, so that we can see you when you're presenting.
Okay. So, okay,
Because they will
enable.
show both your video
Both the same.
as well
Okay,
as
I
the
see. I see. I see. Okay,
presentation.
good. Okay.
Thank you.
Yeah. Okay. So, yeah. Hi. Good afternoon, everybody. So, my name is Siddharth Paranjape, and I'm here in Oschweizer Fachhochschule, that is Eastern Switzerland University of Applied Sciences. And here I will today going to present on an overview of our current activities regarding the steam generating heat pumps for process heating in agro and food sector. And since we are mainly working here in Switzerland, I will present the case studies from Switzerland. So that is the general theme of the topic. Yeah, and this is not just work from my individual work. This is the work of my colleagues, and I am a part of it. So I'm listing some of the names here who have contributed to this work. Yeah. So the first I will start with give you an overview background of the current state of what is in the Swiss industry, what are the demands, what are the boundary conditions, and where we can integrate the heat pumps in the system. So first an overview of the background, and then I will present a rough plan for how we integrate the heat pump into the systems process industry, and a general strategy. And then I will move to considering two case studies that are potential applications for high temperature heat pumps, especially steam generating heat pumps for Swiss industry. I'll give some examples and finally conclude my talk with main takeaway points that we can take from these two case studies. Yeah, so this is the overview for how the process heat demand in Switzerland looks like. This is a data from 2021. The total energy consumption in Switzerland is around for the industry, it's around 43 terawatt hours, and out of which about 20% is consumption in total. From the total, it is 20% in the consumption for Swiss energy industry, and out of which about 54% goes for the process heat, as we see in the left hand side diagram here. And out of which right now we are deriving about 48% of the process heat by fossil fuels. And if we see the industrial sector and classify them, the total process heat in the industrial sector, the top one is chemical and pharma, and the second comes the food and tobacco, and then the rest of the industry. So it is very good incentive to focus on the top consumers for decarbonization and electrification of the process heat in industry. So yeah, and out of this, there is one information that it is not showing on this slide, but about 2.6 terawatt hours comes between 100 degrees Celsius and 200 degrees Celsius range in the process heat. So that's the overall picture of where the process heat demand is and where we can target for decarbonization. Yeah. Then so far there have been many studies, and some of the main are in European Union and USA, that have shown that electrically driven heat pumps, and when it is powered by renewably produced electricity, that is the most promising technical solution for decarbonizing the food and beverage sector. And in case of Switzerland, it is estimated, again I'm quoting some studies here from previous studies, that the potential is about 900 megawatt heating capacity by heat pumps that we can replace with heat pumps by 2050. And that would correspond to the CO2 reduction in the pessimistic range to 24%, on the optimistic range to about 41%. However, to achieve this, it requires many other conditions which are not necessarily technical conditions, such as the favorable electricity to gas price ratio. The lower it is better, of course, and the high CO2 prices, if we can put by policy considerations, then that's good for integrating or giving the incentive to integrate the high temperature heat pumps for food and beverage sector. And maybe some additional policy measures are required to overcome the investment barriers. Yeah, so that's about the electrification for the heat in food industry for Swiss. Then I'll give you some top-down estimate. The same things that I talked, but in the form of a simple table about what the process heat demand is and what are the potentials. And the main takeaway here is that around 2.7 terawatt hours of energy savings can be done with high temperature heat pumps. That corresponds to about 12% of the process heat demand. So yeah, so that's quite interesting and to look forward to. For those who are interested in details, I'm quoting a source here, and hopefully the organizers can share this presentation so that people can directly look at the source of this information, which I'm showing at the bottom of this slide. Yeah, so that's about the potential that we have in Switzerland for energy savings by high temperature heat pumps. However, now we will look at where to exactly look for these processes. So if we focus now on food and beverage industry, there are various processes which require the high temperature heat. That goes from all the way from drying, evaporation, pasteurization, then distillation and cleaning in place, which is not listed here, but that is also one of the main process. And if we see and compare it at what temperature range they are required, that we can see in this chart. So it goes from about 40 degrees to all the way to 200 degrees Celsius, which is very high. And what is the commercially available heat pumps technology that is ready, and at what technology readiness level is available is we can see in the chart. So about up to about 100 Celsius, the heat pumps are available commercially and they are installed. But if we go further for a higher temperature, 100 to 120, 140, the heat pumps are available. They are in the prototype status, but yet not implemented in the Swiss industry in large scale. So they are at a lower TRL level. And if we go further, it is still possible to provide the heat with very high temperature heat pumps, but they are still in the status of laboratory research and functional proof of concept. So that's the picture of which part of the food and beverage industry we can target for decarbonizing the process heat. Yeah. Okay. And I'm here giving some examples of the industrial heat pumps in Swiss food and beverage sector. This list is clearly not exhaustive. It is just representative to give you an idea where the heating capacity lies and what are the temperature ranges, what are the lift of temperature from the, let's say, the waste heat towards the heat supply are needed. And I'm giving some references here for these studies. What we can see here is that when we go to the higher temperature, as expected from the previous slide, the technology readiness level is low. Our case studies are mainly potential applications. Those are not implemented yet, but they are studies that are carried out for that. So yeah, so for the Swiss food and beverage sector, we have already below 100 degrees Celsius, they are already implemented in sufficiently large scale, but for the higher, we still are going to implement it. So this is some of the examples to give you an overview of where the potential is and what are so far implemented. Yeah, so with this overview, we will go now with the, let me present what are the general approach that we took when we integrate the heat pumps in the process industry or food industry. So first one to look at is that what is the industrial plant, the food industry process looks like. So the step is to first gather the data from the process, different processes like what we listed earlier. Then we review the energy and mass balances. And then after going through the details, we first get the data validation, that what we measure or what we take the data from the measurements in industry, whether it makes sense and whether the heat balances are correct. And then we go ahead and extract the stream data, the process stream data for further analysis. And then the next step is we construct the composite curves for the processes that go into the food industry. And they, of course, create the grand composite curve to identify where the heat pump can be integrated. And so basically targeting the energy targeting and allocation of utilities, and where the electrification can be done sensibly. So this is just a schematic view, not the real grand composite curve, but this is typically what we obtain after processing the data, that against a shifted temperature and thermal load, we can see what are the cooling demand and heating demand, and then use the wherever it makes sense, where to integrate the heat pump at what temperature lift, and maybe further an electrical boiler or electrical heater may be needed to get further higher temperatures. Yeah, and then after doing the base analysis, we go for technical feasibility, which involves techno-economic analysis. If it is feasible or not, we try to iterate to see whether we can give a partial solution or full solution, and then the economic viability, and then go towards the implementation. This procedure is quite general and has been adopted, has been used by many other researchers. So this particular diagram I'm adopting from the source that I'm citing here. And we can find it in the other sources as well. Yeah. Okay. And then I will move on to present some simple case studies. 2 case studies I will present to illustrate how this integration has been proposed for the food and beverage industry. So one example is the spray dryer, and in the spray dryers are often used also in pharma industry in Switzerland, and so far they have been using either electrical heater or they have been using oil-fired or gas-fired furnaces. And this particular case study is from a multinational company which is located in the region where carbon neutral or low carbon electricity supply is available. So they wanted to change their spray drying process heating from a gas-fired furnace to heat pump. So the spray drying process required hot air at 200 degrees Celsius, which is dry air at 200 degrees Celsius. And after the spray drying process, the waste air or exhaust air would be at 80 degrees Celsius. And this 80 degrees Celsius humid exhaust air, they were just throwing away into the atmosphere. But then we said that, okay, we could use that as a waste heat and recuperate that waste heat, and with the help of heat pump could be upgraded to bring it back into the drying process. So the left side here is the general schema. So here is the spray drying process, and we could use this waste heat air and go through a recuperator to heat the inlet air. Here I'm putting the minus 10 degrees Celsius as inlet air because we considered the worst case scenario in winter when the spray drying process is taking the air from outside. So this is the worst case scenario. So and then it would be heated to the recuperated heat exchanger, and then further we could use the heat pump to lift the heat further, extract it, and supply. And then we also added a small electrical heater further to fine tune our demand, and also could be used for initial startup process. So left side here is the simple schematic diagram. On the right side, it is more detailed process diagram where we actually would integrate the heat pump using intermediate water circuits, because we want to do the correct sizing of the heat exchanger and don't want to have a contact of the refrigerant circuit directly into the process air, and to minimize the size of the heat exchangers. So the heat pump would be integrated using intermediate water circuits, which will transfer the heat from hot air exhaust to the evaporator, and from condenser to the from the inlet air. Yeah. So, but this is so far I'm just showing the conceptual diagram, but then we went to do the analysis of this process. And first we make the composite curves for the spray drying application. On the far left side is the composite curve for this process. And here we can see how much is the hot utility requirement and how much is the cold utility requirement. And using this, we create the grand composite curve where we actually see the net heating and cooling demand. And we considered two cases. One is we could heat using the standard heat pump using R245FA, and the other one using a transcritical propane heat pump with recuperator, of course. And then we compared these two cases to see which way to go. And it was clear that with the standard heat pump, we have more exergy losses. But with the transcritical propane heat pump, as expected, because there is a high temperature glide on the demand side, the transcritical heat pump gave better COP. And we had therefore more electrical power savings as expected with transcritical cycle here. Yeah. And then we, after considering the transcritical cycle as a main candidate, we again compared for a given transcritical cycle with different refrigerants to see how they compare. And in this case, we focused on what are the main performance parameters to consider. And one of them is here, which I'm here showing, is the volumetric heat capacity, because that determines the size of the compressor and the inlet lines to the compressor. And therefore the propane was turned out to be the winner here, because it is giving us the size of the compressor that is reasonable, and also that can be found in market. And also propane is very cheap compared to the rest of the candidates. And so this was the conclusion of our study, that transcritical transcritical cycle with propane could be implemented as the for this process. But there is one caution that we have to exercise here, is that these are so far potential case studies. It requires further analysis of how much investment cost and so on. The economic analysis has to be done, and that needs to be done further. And it can be envisioned that the economic analysis might show that transcritical cycle with the propane for this application may not be feasible for the given economic conditions. So therefore, we also considered two parallel standard heat pumps, which would provide the heat at two different temperatures in series to the demand side. However, I'm not showing that study here because for the time constraint, and also I would like to give another example before I stop. So other example is the Snap distillation case study. This is again a Swiss company producing schnapps, and the circuit for producing schnapps, this process is a little bit more involved and complicated. Nevertheless, for heat pump integration, we can see that there is one steam boiler and one chiller that is used in the process at present. So we said that, okay, we can replace the steam boiler with a heat pump and use the the cooling water's energy available from the cooling water as a source for the heat pump. And then we considered two cases. One is two-stage cascade heat pump, and the second one is a combined cycle where lower stage is a standard N-butane heat pump. At the upper stage would be mechanical vapor compression of the steam. And this study, I will not go through the composite curves, but this study showed us one interesting thing, that the COP for the combined cycle two-stage system with mechanical vapor recompression gave the highest COP and also very good CO2 reductions. However, again, like in the earlier case study, that these systems are not yet completely implemented and not much data is available for investment cost, at least in Swiss case. So this has to be taken, even though technically they are very feasible, economically the study still has to be done. Yeah, so I think I will not give further case studies. I will just give some examples of heat pumps that are available in the market. One here is the from Swiss company Friotherm. Kobelco is another one that can be used, and another one is sustainable process heat from Germany. And there are many others, including Norway for Heaton, for example. I won't go through the details, that those are available online. And another one is mechanical vapor compression that I just discussed in the last case study, which is also available. So the equipments are available. So the main takeaway from this is that there are potential applications for heat pumps, and essential first step is pinch analysis and do the process analysis to find the correct integration points from the given profile. And here I showed two case studies. The spray dryer case study showed that transcritical heat pump with propane gave the most energy savings. And also for the schnapps distillation case study, a steam generating heat pump was definitely giving sufficient efficiency increase, which could lead to actual integration. Again, but to caution that for presented case studies in Switzerland, the heat pumps are not yet implemented to date. And so there are many barriers for implementation. The first is lack of know-how for these technologies in industry. and the paneling tools and training and demonstration cases, so non-availability of demonstration cases. So those are the barriers to actually go into the market. But the outlook seems good because there are more questions coming about how to implement this thing in the industry. Yeah, so we have to investigate the constraint and distances between the heat source and sinks, the safety aspects, retrofit options, and economic analysis. Yeah. So with this main takeaways, I would like to first acknowledge our partners and Swiss Federal Office of Energy, because of which we could carry out these various case studies and research. And finally, thank you for your attention. And this is our team, which has been working on different aspects of the heat pumps. Yeah, so thank you very much.
Thank you, Dr. Paranjpe. I think you have left. Have you left?
No, I'm still here.
No, we want to ask one or two questions, and also
Yeah,
you
sure,
are
yeah.
not been introduced. So I would
Yeah.
like to introduce you.
Okay, thank you.
Dr. Siddharth Shankar here. We
Yeah,
missed
thanks.
formally introducing you to the audience. We would
Okay.
like to do that now.
Yeah.
Dr. Siddharth Paranjape specializes in the design and mathematical analysis of fluid mechanics and heat transfer engineering and experimentation. His professional experience includes developing phenomenological models for engineering systems and planning, designing, and executing engineering experimentation involving energy conversion systems. He also offered technical consulting services to the industry. Thank you for your talk, sir.
Siddharth,
Thank you.
there is one question from audience.
Yeah, this is Sukumar Devota. See, you made a presentation on Schnapp distillation.
Yes.
But in that, why didn't you consider either mechanical vapor recompression or thermal vapor recompression? You could have considered, because there will be water at the required, you are using steam, so you can compress, evaporate water from the using the condenser on the top. It's only about 90 degrees or so, and you can compress it to get it something like 105 and supply it to the reboiler.
Okay, let me see if I can understand your question correctly. Because, okay, can you see my screen yet?
Not screen. Yeah, I can see you, but not your screen.
Okay, let me see how to change this, because I want to show the diagram to the audience as well.
Now you can give it some oral answer,
Okay.
because they have removed this screen. I
Yeah,
think they have put the next
Dr.
one.
Siddharth, we can see your PowerPoint screen now.
Oh, you can see. Okay, I see. You can see my PowerPoint?
Yes.
No.
Yes, we can do that. If you want to go to a slide, you can go ahead and show.
Okay, only thing is I'm not able to. Yeah, here. Okay, here. Let me see if I can
Share your screen,
Can you see my screen now?
I think Siddharth Javata will contact you, and then so basically the vapors can be compressed and then their heat can be used. That is also one of the things, because you have not built the system, I think, yet. So then you
no, it is not built yet. It is still in the conceptual stage. Yes.
Okay, then. Thank you.
Right. Yeah.
Thanks a lot for your excellent presentation.
Thank you.
Next line is, so next one is CO2 heat pumps for process heating and cooling. Yeah. Okay.
So sorry, I didn't understand the question. Could you say it again?
No, I think we can, we will correspond with you over. The next speaker is already ready. So
Okay, I see.
I invite Professor Trigwe M. Aikivik. Sorry, my present name is not properly pronounced. please welcome you. I think they will introduce your
Talk number 245, heat pump technology for drying applications in agro-food sector, Professor Tregve, Norwegian University of Science and Technology, Norway. Professor Tregve is a professor in the Department of Engineering, Energy and Process Engineering at the Norwegian University of Science and Technology, Norway. He works in areas of refrigeration and heat pump systems, specializing in high temperature heat pumps, snowmaking systems, and energy efficiency in industrial processes. He also works on heat pump assisted atmospheric freeze drying and fluid bed dryers in combination with microwave and infrared heating and mechanical and ultrasound vibration. We welcome you, sir.
Thank you very much. And thank you also for giving this speech here at Refcold'. And I'm very happy to talk about this topic. I have some few points that I like to look into. I will first say something about challenging some of the emissions, CO2 emissions and energy efficiency, excess of heat in industry and possibilities. I will not use very much on this, but also take most of the time on heat pumps principle, working fluids. I will not go in detail as Armin Hafner, but I will show something and give you some examples. We see very often when we are talking about heat pumps that there is a very little understanding of the quality of the product, because the quality of the product can highly be influenced by the process you can tune by the heat pump. This is colors, flavors, texture, density, and shrinkage. So by changing temperature, changing the relative humidity, and also air velocity, you can change these parameters. Because I see sometimes that they make drying system and they include a heat pump, and the heat pump is normally put in like just to recover a little bit heat, and you take most of the heat or energy from the ambient. So this is a challenge when you are doing with a heat pump. You should have a closed loop. Don't open it up, because then you have influence from the ambient. And to have the high energy efficiency, the high smear, you also can do this with running the heat pump. Another aspect is the environmental aspect. If you use green energy for the heat pump, you reduce all the emissions from your heating system. So that makes your green system if you can have green electricity and use a heat pump for the drying process. Open systems, there you have temperature and relative humidity variation, and that you have not totally control of your quality. I like to use this diagram or this curve. We have normally hot air dryer. You can use ambient or use the sun, or you can have boilers or whatsoever that are heating your drying. It gives you a low quality, and you have a low cost of your system. And on the other hand, that you have the vacuum freeze drying gives you high quality, but it's a high energy consumption. It's a high cost of the system. The heat pump, you can design between the vacuum freeze dried products and the hot air dried products. And that gives you new opportunities. You can tune in products into the market that has a higher quality, and you can take a better price. So you are afford to run or buy a heat pump by doing this type of system. So typically the heat pump dryers, they are in the temperature range here. Vacuum dryer at low temperature, and you have a lot of dryers on the other end. But nowadays we see also, and the previous speaker was talking about the high temperature heat pump. The high temperature heat pump moves this process upwards in temperature, and that gives you all new possibilities. Maybe not in agri products that are a little bit limited by temperature, but you can do example he did. I have also an example of spray drying for milk with the heat pump. I will come back to that, not in details as before. So closed loop, you have the atmospheric pressure, you have full control of the temperature and relative humidity and the air velocity. And then you can influence by tuning these parameters. You can influence on the shrinkage, the rehydration ability of the product. Normally you have a dried product, you like to rehydrate. So the time it takes to rehydrate is highly dependent on the temperature level you are drying. The color, taste, and aroma. And you have the possibility to dry from some minus degrees Celsius. Then you have quality like the vacuum freeze dry and upwards. I just like to also point on this diagram. This is a little bit old. It's from 2015, but the World Energy Outlook comes with these reports every year. So you can follow how the area is. But I like to point on the light blue. The light blue is how you are running your process more energy efficient, reducing the primary energy consumption, reducing oil and gas consumption. That has, in this diagram, maybe 40% of the reduction of CO2. So it's a more a question, how efficient can I run my process by energy, such a way that we contribute also to the reduction of the emission of CO2. This is also one paper that's been launched in Europe. I just want to point on the drying, and we can see that the drying is typically for the processes today from about 40 and upwards, and there is a lot of possibility with existing technology of heat pumps up to 100 degrees, but there is a huge potential also in the area above, typically then for the drying, for example, milk drying. And the potential is huge. We can see that in terawatt hours, this is Europe and the countries in Europe. And we can see that if you take only the area from 60 or up to 150, you have in the food and the tobacco industry about 175 terawatt hours, only in Europe. That's huge. And if you want to reduce this and transfer to heat pumps, there is a huge, huge market for heat pumps. And if you take the potential, it's 3,126 pecajoule. That's a lot of energy. If you take just a part of this, it's a lot of heat pumps that are possible to build. Maybe not only in the agri area. Then I like to focus on the COP of the heat pump. So if I do it very theoretically, just look at the temperatures and use the Carnot process. I have the Carnot process in the bottom. This is my cooling temperature, and this is the hot temperature and the cold temperature. I can calculate COP of my theoretical process. And if I take my process, the real process, the cooling, because when I do the heat pump system or have a closed loop, so then the energy I have to cool and remove the water before I'm reheating. So I have the cooling capacity and the energy of my compressor or pumps or fans I put in. You know that if I take the ratio between the process COP and the Carnot process, it's in the range between 40% and 60%. So if I calculate with 60% of the Carnot efficiency and look for the temperature lift and different temperature, it's -10 up to plus 70, do you see that if I have a lift normally in such a drying system, 15 to 30, I can have a COP of my system more than 6. Very high COP. And if I look for my smear, I take my COP, divide by the enthalpy, divide by, so this is energy for per gram or kilogram of water. So the enthalpy from the Mollier diagram, and I find the smear, and the smear can be really high. It can be from 2-3 or up to maybe 6-7. Maybe 6-7 kilo water per kilowatt hour. So it's a huge potential for the drying process. It's more also a question if this is the calculation I did some years ago with ammonia as working fluid, and I'm looking for the relative humidity at the inlet and the outlet of the drying chamber. And you can see that for different inlet temperatures, you have an increasing value of the smear just by design. And there is an optimum in the Mollier diagram, there is an optimum design. So when you are doing design of the heat pump for the dryer, it is the evaporator that's the most important. Because the evaporator removes the water from the cycle before the reheating again. This you all knows, the cooling capacity and the heating, and I just wanted to make this as a point that the energy you are removing in the cooler, you have to put back in the condenser or in the heater, and this is bigger than this one. So there is an excess of heat. So keep that in mind. If the system is well insulated, you have to remove some of the heat for something. And then you can remove the superheat of the working fluid, and that makes a possibility for heating hot water. Very often the food industry, they have a need of a lot of hot water for cleaning. So you can have for free all the water for cleaning, and or you have a free drying process. So there is a lot of possibility to combine, and the temperature levels. This is the inlet air temperature of the dryer. This is the exit temperature of the dryer. This is the exit temperature of the cooler. And that means you have an evaporating temperature lower than this point C, and you have a condensing temperature higher than point A. So this is the temperature difference or pressure difference for your system. Some few words about the working fluids. Armin has looked into that when it's starting and so on, and the change from ozone depletion and global warming, and now acidification of water. But I like to point on Gustav Lorentzen, Armin Hafner also pointed on this. This was a statement he made in 1987, and I like to just read the red points. It must be obvious to use natural component known to be harmless. Why should we have new component that we don't know the future? We don't know how it will influence on the human people. Then I like to point on the same component, but I have one more thing that Armin was not mentioning, mixtures. When we are doing drying, we have a temperature difference we are cooling in the air in the evaporator, and we are reheating in the condenser. And that's a big temperature difference. It's a big temperature glide. If I mix, for example, a hydrocarbon with a few percent of CO2, big difference in normal boiling point, I get a fluid with a big glide. That's more suitable for the cooling and are more suitable for the reheating of the air in the dryer. So mixtures, this is ammonia water. I will show just a brief mention this. This is also excellent for example, for pasteurization of milk. Because the milk is coming from the cooling or from the collecting system at +4, and you heat it up to 75, and you are cooling it back to +4. You have a heat exchanger between, but you need a heating, you need a cooling. This system is also giving a big temperature glide that gives a possibility to have a very energy efficient way of heating and cooling, for example, the pasteurization process. This is some new fluids from 2008 to 29. Blends or pure HFOs or mixtures. This is also, I don't know if I lost my reference. This is till reference till atmosphere conference. They have listed a lot of these fluids. You can find that the fluids on the list here. That's are these PFAS fluids coming. Then just to show you the simple system, this is a fluid bed. You can have a tunnel the dryer or whatsoever you like to put on this side. You have the fan that's circulating the drying agent or air, and have a filter so you don't get dust on the cooler. And then you have the heat pump internally in the process. You have to cool the air so you are below the dew point to remove the water, and you have to reheat the air back to the inlet of the dryer. And then, as I mentioned, there is an excess of heat in the process. You have to take this out of the system, for example, for hot water drying. It is also possible to have a heat exchanger between the air coming out of the dryer with the air after the cooler. So I'm cooling down as part of the air here with the warmer air here, and then I have a possibility to reduce the size of the evaporator. In reality, I can reduce the size of the heat pump up to 50% just by an internal heat exchanger. And this just to illustrate on the Mollier diagram. I just like to show you a factory we made for some years ago in Hungary, up in the northeast of Hungary. It was designed to dry sweet corn and peas, green peas. It was made with a step-up temperature. So we had, as you see here, there's a fluidized bed. So this is a big fluidized bed. I have a better picture here. The low temperature dryer, it has one layer, -5. So we had a freeze drying of the sweet corn. And when it was coming below a certain level of humidity of the sweet corn, we transport it with the pneumatic. There is an exit from this fluid bed. Go back here to new dryer, 6 meters in diameter, and had +25. So I had the final drying at +25. And we made a quality of the green peas and the sweet corn similar to freeze-dried product. I will also mention a possibility also for different, this is for different products. If I have an adiabatic dryer, typically that I've shown before, when you are entering the dryer, you are removing water from the product. You are ending up, depending on the water activity of the product, as a maximum. But if I'm able to put some heat into the drying chamber, I can improve my drying capacity of the heat pump system with the same air circulation. So instead of ending up here, I'm ending up here, and that means I have much higher water removal of the system. So this can be just shown. This is 30% relative humidity at inlet, 90% at outlet, and different temperature at inlet of the dryer. We see that we can have a relatively high extra capacity of the drying system just by heating the system, adding heat into the drying chamber. This is an example we made in the lab. Now it's in a factory in Trondheim. It has 2 drying chambers, the dry fluid bed and the wet fluid bed. the air is circulating, we're removing the water. We have one condenser for reheating coming into the dry chamber, and the product is going counter current and coming out on the other end. The air is then going for cyclone to remove dust and particles. We have the superheat. This was an ammonia system. So we have the superheat from the ammonia system. And then we had also an extra condenser in the wet bed for drying. And that make this design and that we had in the lab increase the efficiency of the drying system 4 times. 4 times more efficient system. That means if I go back to this curve, I was here about 4. So number of efficiency of the circulation. Just to show the possibility also for heat recovery, I have an example with a CO2 system. If we are going above the critical point, I will have a transcritical process. So I have a huge temperature glide of my system that I can put in. No, that was the wrong one. It is one. This is a drying chamber. So the product is on the racks. So I'm circulating. And this is also a question of the absorption isotherm of the process. And if you have a process that goes very slow, the water removal from the product is slow. That means that you normally then circulate too much air in the system, and you don't like to condition the air for the total airflow. Then you can take, for example, 20% of the air, cross heat exchanger, cool it in the evaporator or removal of the water, then reheat and have a heating. So you have a kind of an external heat pump system for your drying system. And if you use the CO2, you have also a possibility for preheating of the water, since you have this temperature glide of the system. Yeah, I think I skipped this. This is a system for pet food, drying of pet food. There's also a product from a lot of the component in this type of system is from agriculture. So you might make your composition of the pet food, you extrude it, you get pellets, and then you dry it in a superheated steam dryer. And then you can use, for example, you are circulating the steam. You are reheating the steam from 110 to 180, and you have a vapor compression system with turbo compressors. And you can have a heat recovery of also this system by condensation of the water at 110 degrees. Yeah, I have some example. This is the spray dryer. Then I will lead you back to this mixed fluid, hydrocarbon with CO2. And then I can have a perfect glide in my evaporator and in the condenser that are suitable for the heating of the air before it goes to the dryer. And you need very little reheating at the end. This is the system that's shown also from the previous speaker. But here also you have got this glide. This is a mix of water and ammonia. You have a glide on the low temperature and the high temperature that could be easily fit to, for example, a spray dryer. So integration of heat pump gives a lot of new possibilities. You have full control, temperature and relative humidity. That means that you have full control of your final product. And the heat pumps in industrial process will have a huge impact and be very important in the future, both for energy efficiency and for reduction of CO2 emissions. and smear values for heat pump system, depending on you going very low in temperature or high, you will be between 1 and 6. And natural fluids are very suitable for most of the systems with drying systems. And also heat pumps with CO2, very easy to have energy recovery and hot water production. Thank you.
Thank you, Professor Aikuvik. And I request Dr. Didier Coulomb to give a memento. Thank you very much once again for the nice lecture. Now we are coming to the last talk. That is on heat pump for cardamom drying by Mr. Jai Prakash Gurusamy, please. From Train Technologies, Bangalore.
Talk 246. Heat pump for cardamom drying. Mr. Jayaprakash Gurusamy, Train Technologies, Bangalore. Mr. Jayaprakash Gurusamy holds a master's degree in thermal engineering, refrigeration and air conditioning, and a PGDP operations from IMT CDL, Ghaziabad. His expertise is in refrigeration system design for commercial and transport applications, HVAC and refrigeration equipment rating standards, test lab design, operation and calibration, and field service engineering for transport and unitary HVAC systems. He is a certified professional in carbon footprinting by CII Hyderabad and a certified Six Sigma Green Belt from LG Electronics. We welcome you, sir.
Thank you very much. Yeah. Good evening to everyone. And first of all, it's a great privilege to talk in this excellent forum, and thank you for organizers to give this opportunity. And I see, I'm really proud to talk here. I've seen a lot of speakers, eminent speakers before this actually on this topic. And this is going to be on the a real case study on drying of the cardamom actually in the Western Ghats of India, in the Kerala, state of Kerala actually. So I'll go into next slide. Yeah. So before that, I'm just giving an acknowledgement for, I was working with some of the companies, helped us in understanding, studying the, like E3 Agro Solutions for studying the cardamom drying process, and for Train Technology myself, and IceMake, who has supported in manufacturing installation of the prototype actually. Okay, so let's start the story like this. So this is called the Marihattan Solar National Park in the Kerala's Idukki district, around 2,200 meters high. And just below this, around this area, a lot of cardamom plantations are there. And traditionally, cardamom is grown. There's a cardamom plant. Cardamom is dried after the harvesting using the firewood. And most of the firewood comes below this, the nice national park, and it's getting a lot of things are happening over there. We are using a lot of even outside wooden pallets and at all. Still, we are just keep on removing the wood. So we thought, like, why not we find a solution? We can replace a heat pump here instead of having a firewood based this kind of dryer for cardamom. So that's the story here. So let me give a background. So green cardamom, which is called as a queen of spices, grown largely in the southern states of Kerala in India, and grown in the Western Ghats in the high ranges of the evergreen forest. And raw cardamom is traditionally dried using the firewood furnace from trees or briquettes. Briquettes means compressed wood actually. And this project is an attempt to electrify the cardamom drying process that can save the environment and also can reduce the firewood cutting from the forest and save the carbon footprint also. So you can see this is the cardamom plant. And from there, cardamom plant, there's a fresh green cardamom. And after that, it will go into the wood-based, firewood-based furnace dryer. And one important thing is here, within 36 to 46 hours, we need to dry it. Otherwise, it will lose its aroma and color. So nowadays, within 24 hours, we have to dry it immediately after harvesting. We cannot store it. After drying only we can store, and that's a dry cardamom actually. This is the process in a cardamom drying. And if you see the traditional furnace wood dryer, you can see the fuel is briquette and firewood coming from the forest. We have a furnace where fossil fuel like or wood fuel with a blower, and there's a drying tray or bed, and that will all the air will go in exhaust, and some of the air will be bypassed only at the end of the process. Rest all will go, and this combustion is almost only up to 40% efficient actually. Very inefficient process, and a lot of smoke is there, and a lot of inconsistency in the process. So some of the, if you see that machine, there's a furnace dryer at the site, actual site, using the wood, firewood based. Key drying parameters, you saw that cardamom, initial moisture around 83 to 87%, and we have to dry it to final moisture of 10 to 12%, approximately 10%, and drying time for one batch of cardamom. This dryer, what you are seeing in furnace dryer is around 500 kg raw cardamom we can process, and you have to dry it at least for minimum 18 to 20 hours, and then you will get the color of green fresh cardamom with a good aroma, and expected wet to dry ratio 5:1 to 6:1, depends upon if the cardamom pod is very good matured, you get a good weight, and it is very less premature, then it will be 6 weight. So 5:1 to 6:1. Temperature requirement, which is very key here, 45 to 65 degree. We go up to 70 to 75 at the end of the stage, but average 45 to 65 degree. And we have to maintain increasing the temperature stage by stage actually. So you can see that actually here. And these are some of the standard wood briquette furnace dryer. There is the furnace, what you have seen, the dryer initially 500 kg capacity. Initial weight of raw cardamom 500 kg, moisture content 86%, final moisture 10%. Approximately 422 kilogram of water has to be removed, and the amount of wood or briquette required is 180 kilogram of material. The total caloric value, I considered 4,000 kilocalories per kg of briquette or dry wood, which is around 720 kilocalories. Drying time per batch 20 hours, and the blower motor we have like around 2 HP, which is 30 kilowatt hour, 1.5 kilowatt into 20 hours. And smear specific moisture extraction ratio is 0.487. That's what Professor talked about just previously. And the smear is a key metric that provides the amount of energy required to remove the required amount of moisture. If you see, if I consider furnace dryer 100% efficient, then the smear will be 1 actually. 100%, it may not be possible. So it's all, my case is like only 40%, 45% efficient. So it is showing 0.487. For a heat pump dryer, what we have, it's showing around 2 smear. Normally, even if the worst case scenario, it will be 1.5 and above. We have seen 2 to 3 average in this kind of drying application. And these are the some of the firewood available there. And also along with the firewood, nowadays we are getting briquettes, because firewood is more and more government having a lot of, we cannot get the firewood easily. So briquette is there, but briquette is very costly also. So what we did is, along with that, our company E3, so we studied how the cardamom is really dried actually. The cardamom is dried, and every stage of the drying, we measure the temperature and relative humidity. The disadvantage in the furnace side is we are controlling only temperature, that too by manually adjusting the temperature. Like in 20 hours, evening 5 o'clock, they load the cardamom till next day, evening 3 o'clock. So overnight, the labor he will not sleep. Every 2 hours, 3 hours, he has to adjust the temperature, but he don't have the control on the humidity actually, relative humidity. So slowly he has to dry actually. So now this one curve, we did a lot of trials, and we could able to see there are 3 zones of drying in the cardamom. One is initially the zone is warm up and constant drying rate period. The second zone, falling rate drying period, and the third is the target moisture drying period. Okay, these are 3 specific zones. And you can see in the second one, drying curve generated with the different set points. If you see the peak moisture coming at the second stage of this, okay, and that's where we specifically had to design our system to get that moisture, okay. And this moisture, this drying kinetics curve can be different for different products. Once we study on the like for example, pineapple or apple or kiwi fruit, or this is for cardamom actually. So, and also once we know, and we can make a lot of trials with the different set points of temperature, different set points of relative humidity, adjust and generate the curve. And certain point of curve, we could able to see, okay, this is the curve where we can get the cardamom quality better, good quality, and we can maintain the same kind of temperature and control. That's where we get the control and we started putting in an algorithm, and our controller is now doing that work automatically. So that's why we studied from this actually. And if you see the schematic, it's very simple. I think we have seen a lot of presentations earlier, how the detailed schematics, but you have a raw cardamom dry bed, condenser is there, hot air is going into the raw cardamom, and warm air is coming out, warm and humid air is coming out of the cardamom bed. It gets into evaporator, but not all the get into evaporator. Some are bypassed. In fact, this is the first photo we did. We can use a heat recovery where the bypassed warm and humid air, and we can exchange that. And once again, we can return back to the condenser. This kind of heat recovery also we can use it. And we have an auxiliary condenser to control the temperature. And the first prototype in October 2021, actually, how it happened is like in 2020 during COVID, when we get locked down after initial open, and we got stuck over there, and like many times we spend, and that time we spend usefully to analyze this information. So we could able to make a prototype with the help of the manufacturer. And if you see here, the total moisture removal rate is around 85 kg, drying time 20 hours, maximum temperature 70 degrees Celsius. We used R134 because that's the readily available compressors. I was talking to Professor earlier, and he talked about we have to move to the new refrigerant, low GWP. Our next prototype, we already in discussion, will be R1233ZD, or we'll be moving to next to propane also. So R123ZD is our GWP is 1, and propane almost 0, right? It's 0. So that's our next new plan actually. So because it's immediately available, we took this in India, but once the compressors are available, in fact, I was talking to the manufacturers, they are already working on the prototype with R123ZD and also propane. So once those compressors are available, we are going to have this inside. And you can see this is our first prototype for the heat pump cardamom dryer. And we have this excellent quality and color. And we have this control panel where we have this algorithm set in. This algorithm is set in based on our drying curve analytics, kinetics, and based on that, we can able to control the temperature and RH, unlike our furnace dryer where we can do only temperature control. And then we come up with by seeing this success, we come up with a second prototype. We installed in September 2023, not 2020, it is 2022 actually. Yeah, commissioned in September 2022, and we already processed 2 lakh kilogram of raw cardamom till September 2023. 750 kilogram drying in 18 to 20 hours, total moisture removal 603, and total avoided emission. Okay, I just giving a caveat. I have not considered R134A gas into the emission, but all other emissions I have considered. 71,200 kilograms CO2 emissions we avoided. If you see the ratio of emission reduction with respect to furnace, it is around 46% lesser actually. These are our second prototype with the controls and everything. We have the enclosed ref system, then air side blower, cardamom drying bed. And if you see the top, there's a 2-fan external auxiliary condenser. And that ducting system is a heat recovery plate heat exchanger, cross flow plate heat exchanger, where we can recover the hot humid exhaust here. Some sensibly will recover. So it will not, fresh air will come without mixing with the exhaust, humid exhaust here. And this is our touchscreen PLC control. And it will, in fact, our farmers are somewhere there, 500 kilometers away. I'm sitting in Bangalore. Vinod, he's there. He's from E3, sitting in Chennai. We could be able to see in our mobile only, and we can see some error codes or sometimes there's a HP or LP trip, we'll get error code. We are connected to IoT also. Okay, now the drying process, the wood-based, briquette-based drying process versus heat pump. What is the advantage? What we are getting? The picture what I'm showing here, heat pump, that cardamom, and below wood dryer, you can see the clear difference actually. Yes, in furnace also you can get it, but you need to be very skilled. Okay, but if you are just doing, you can see the color, inconsistent color with some kind of burning. Sometimes smoke contamination will be there because we are using firewood. Here that problem is not at all there. We could able to program our algorithm through the drying kinetics curve, and our process is very consistent, fresh, uniform color, and it's fetching higher premium price. Today the cardamom price around 2,000 rupees per kg. In average action sale, this if a furnace is going around 1,800 rupees, I can per kg 150 to 200 additional premium it can go. See you can see this is a real actual site picture actually, and better weight, average weight ratio. And also another thing, as Professor mentioned, we are not exhausting. If you see our first schematic, all we are exhausting. Once it is drying, it's like one way through. Fresh air comes, heat in the furnace, it will exhaust. We are not returning back, we are not recovering. Here we are recovering that, condensing it. So we are retaining the oil retention and aroma also. We are retaining much. And that oil retention capacity is much higher in the heat pump based drying cardamom. That is one of the biggest advantage we are having. And we are having fully automated, and our drying processor controlled through the PLC controller. If it's the wood dryer, we have briquette loading, manual adjustment overall night. We have smoke contamination sometimes into our cardamom final product. The biggest another problem, we have to dump the ash every day morning. We have to clear every day evening. We have to clear the ash and we have to dump it somewhere. It's also going around that jungle area actually. So that's one of the hazard we are having here. And investment and ROI, yeah, we studied a lot and see, like as a farmer, if I want to install 500 kg dryer with a wood furnace, wood-based drying, the capex is currently we studied and it is 2.5 times higher. Heat pump cardamom dryer is 2.5 higher capex is there, but operating cost it is only 50%, 0.5x. And CO2 emission minus that R134A, assume that is a eco-friendly refrigerant, 50% less CO2 emissions we are actually having. And ROI, when we calculated less than 2.5 years, considering it will not run for 365 days, we run only for 9 to 10 months, around 200 days. We consider 200 days. So the ROI will be 2.5 years. Now, as a farmer, maybe if I have 30, 50 acres or 100 acres, daily I'll use. But if I have only 10 acres and I can actually rental, I can make this a service model. So other farmers, I can do it. Today in the market, with the furnace, firewood furnace, they are charging 12 rupees per kg. Actually, their operating expense is 9 rupees. But in the heat pump, my operating expense is 4.5 rupees only, or minimum 4 rupees only. Okay. Now, in that case, if I use a service model, my ROI is going to be 1.5 years. So that's the advantage we are getting in this actually. So if we see sustainability, CO2, so the same, we just, even though farmers are trying to get the briquette, if you see the briquette price are keep on increasing. So as the briquette price are keep on increasing, farmers are trying to get the wood from the nearby that national park forest actually. So it can get into there actually. So today I considered only 30% of forest wood usage. In fact, earlier they are using much, much higher. But the way the briquette prices are going up, they may use much more wood also in future. So I consider only 30% of forest wood usage, around 20 tons of CO2. And for one dryer, I consider everything for one 500 kg dryer, 22 trees of 1 ton of capacity. 1 ton tree means I consider a tree of 15 years old can give 1 ton capacity of wood. Okay. That 22 trees of 1 ton per year, I need to consume from the adjoining forest. Considering the transportation briquette, wood furnace, so my total emission is 66 tons of CO2 per year in the atmosphere. By using the heat pump, I consider grid factor from our government website. Below I have given the reference, 0.76 kilogram of CO2. I listen to all professors. They are from the Switzerland and Norway. They are actually it's 0.35 kilogram of CO2, unlike us. So if we use renewable energy, like I mentioned there, it can be much less, a 0.2 or 0.3 kilogram like solar energy. It will be like only 7 tons of CO2 per year. So this is the miracle of, I can say, the heat pump usage actually. So the impact of electrifying the cardamom drying process. So as per Spices Board information, every year 23 tons of dried cardamom is produced, and these are statistics for 21-22. Okay, 23,000 tons. Average, if you see, 22,000 tons of dry cardamom. That means you multiply by 5.5 or 6 times, that much raw cardamom we are producing. So 20 tons of dry cardamom processing needs approximately, in the Idukki district of Kerala, I can say around 500 kg capacity firewood furnace dryer, around 1,000 to 1,200 furnaces are there actually. And if I consider 30% of tree wood cutting and 70 briquette, every year we need to cut 23,000 of trees, approximately, which is equivalent to you take 1 ton weight of a tree, then it should be 23,000 trees has to be cut. Yes, somewhere we are losing it actually. And this is going to come from the same forest zone that will threaten the flora and fauna of the Western Ghats. And additionally, 22,000 tons of CO2 also released. Of course, there are some, I used to listen like this biomass wood, they are carbon neutral, but it will take 15 years for a tree to grow and absorb all the CO2. but within overnight, we are just burning it. So it's like even the carbon neutral, the time factor is too large. Overnight, I'm burning 1 ton wood, or 2 nights, I burn 1 ton wood, but it takes 15 years to absorb that carbon. That is the implication. And finally, summary, the cardamom dryer is on the verge of change to a sustainable way of drying, and it will decarbonize the drying process going forward. And this is a starting point. We actually, this is the first kind of project in that area. Of course, there are lot of things they are trying, but we demonstrated, this is the first time we did in that zone. First time we demonstrated to farmers, this is really good, we can help, and they are moving forward now. So awareness, what are the actions? Awareness and government policies can help shift faster to sustainable drying methods. Subsidies and loan policies, we are actually identifying, and training on heat pump and availability of skilled technicians in those areas. So, and finally, I started the slide with the national park, and this national park can continue, thrive with flora and fauna for future generations by taking meaningful actions on environment today. So this is my summary. Thank you very much.
You, Jayaprakash, please be there. So, yeah, it was very nice. And then maybe I will myself. So that brings to the end of this session. There were 6 talks, and I don't want to summarize them because all of you have already known. And then we learned a lot about heat pumps. And I'm very glad that heat pumps are coming back, and particularly for food applications, which is, in fact, I did my PhD 50 years ago in the same topic of food processing, and that too with heat pumps. And now I am again, after 50 years, chairing a session on that, and I'm very glad about it. And then I thank everybody, all the speakers, for their excellent presentations. And even I learned something after 50 years. Thank you very much. Thank you. Please stay on this.
Ladies and gentlemen, it's been another day of intense technical knowledge sharing. I'm thankful to all the speakers, and primarily for the session chair of today's afternoon session. I request Dr. Sukumar Devota to please come and share with Professor Srinivas Murthy our memento of gratitude for chairing the session. Thank you so much, sir, for chairing our session and making it special for us. That brings us to the end of the second day of the conference. And tomorrow morning, the session starts at 10:30, not like 11, like what we started yesterday and today. Tomorrow morning, it starts at 10:30. And we have interesting sessions for tomorrow morning as well, and an interesting panel discussion too. So I invite you all to join us for tomorrow. And that's it for the day. Take care. Bye-bye. Have a good evening.